This is Lesson 9B, Unit 11, calculating the pH at the equivalence point for a weak acid. So what we have done so far is we've determined that our initial pH was 2.20. Then we did another calculation at 15 mLs and we determined the pH was 3.03. And then we did another one at the very special point, 25 mLs, for this particular titration that is called the half equivalence point, where pH is always equal to pKa. What we're going to be doing now is calculating the pH at the equivalence point and explaining why it is always greater than 7 when we are titrating a weak acid. So we've got 50 mLs of 0.1 molar sodium hydroxide and 50 mLs of 0.1 molar of the nitrous acid. And we're going to go ahead and set up a before, change, and after table in millimoles because the reaction is going to go 1 to 1. So we've set up to determine what our limiting reagent is. And as we go through, we have equal molar amounts of both of these. This is the equivalence point, equal molar amounts. So we're going to use up both of these completely. So minus 5.0, minus 5.0, plus 5.0. We don't care about the water. So we have none of the nitrous acid left. We have none of the hydroxide left. And what remains is 5.0 moles, or millimoles, of the NO2 minus. So this is going to go to equilibrium. So this goes to equilibrium. Which brings us to the second part of the problem. We're going to end up setting up a rice table. So we have 5 millimoles of the NO2 minus. This is going to go to equilibrium, so I'm showing the equilibrium that will be established with water. And notice we're going to be producing some hydroxide ion. Now, for the ice table, we have to be in molarity since this is at equilibrium. So we're going to figure out the concentration of our NO2 minus. So we have 5.0 millimole over 100 mLs. And when we go to figure this out, this is 0.050 molar. So we can go ahead and put this value here right into our initial concentration. So we have 0.050. We don't worry about the water. Initially we have 0 of each of our products. We are going to start losing reactant and making both of our products. So we end up with 0.50 minus x, x, and x. Now, notice that I am making base here, so I need Kb. And that's because I have the hydroxide ion is my x. So I'm going to take 1 times 10 to the negative 14th. I'm going to divide that by my Ka value, which is 4.0 times 10 to the negative 4th, which is going to be equal to 2.5 times 10 to the negative 11th. All right, I can assume that x is very small compared to 0.050 molar. So I'm comparing it to this value here. So I have that 2.5 times 10 to the negative 11th is approximately equal to x squared over 0.050. Remember that x is equal to the hydroxide ion concentration. And when we solve, that's 1.1 times 10 to the negative 6th. pOH is equal to 5.95, so pH has to be equal to 8.05. So now we have that the pH is equal to 8.05. In terms of what we have in solution at this point on the titration curve, is our solution contains mostly the nitrite ion. So our solution contains mostly NO2 minus. Now we're ignoring water. This is characteristic of the equivalence point for titrating a weak acid. Is what you're going to have remaining at the equivalence point is the NO2 minus, because if we go all the way back up here, what we have done is the reaction has gone to completion at the equivalence point. So we're going to have mostly NO2 minus at this point. So if we come back to our titration curve here, at this point right here, HA equals A minus. At our equivalence point, it's almost all A minus. If we're on this side of the half equivalence point, then we have more A minus than HA. And if we're on the other side of the equivalent point, let's see, how am I going to show that? We'll do that. Not very classy. Our A minus is less than HA. We have more of the HA. So now we have completed the titrations at no added base, 15, our half equivalence point, and then we've done our equivalence point. We've got one more point we're going to do, and that's going to be somewhere up here. All right, we are on our last titration calculation for titrating a weak acid with a weak base. We are going to be going the other way next, but we're almost done with this. So we have calculated the equivalence point in the last calculation. Now we're going to calculate past the equivalence point, somewhere up here. So we've got 60 mLs of 0.1 molar sodium hydroxide, 50 mLs of the HNO2. Our total volume is 110 mLs. We've added a total of 6.0 millimoles of the sodium hydroxide, and we've got 5 millimoles of the base, of the weak acid here. This we're going to assume goes 100% to completion, so we're just going to complete the BCA table. So minus 5.0, minus 5.0, plus 5.0. We have none of the acid left. We have 1.0 millimole of the hydroxide, and we have 5.0 of the NO2 minus. Now, when we go to calculate the pH, go, should I set this up in an equilibrium with water? Well, this is only a very weak base. We've got a very strong base present right now. We've got our sodium hydroxide present. So NO2 minus is a weak base compared to the hydroxide. The hydroxide ion is going to control the pH. So hydroxide controls the pH. Now notice that I put the brackets around the hydroxide. That means we need the molarity. So the hydroxide ion concentration is going to be equal to millimoles of hydroxide over our total mLs. And so that is going to be equal to 1.0 millimole over 110 ml. And when we calculate that, our molarity, before we do sig figs, is 0.00909 molar hydroxide ion. We're going to calculate the pOH, and After that, we'll calculate the pH, and it turns out that our pH is equal to 11.96. And there we've got our final answer. Okay, one of the things that the AP curriculum expects you to be able to do is to characterize the major species that are present at each point along a titration curve. So this kind of summarizes what we've just finished doing. In this case, this is the titration of dilute acetic acid, and it could be any weak acid, so we're going to just call it HA, with sodium hydroxide. And we want to identify the major species that are present at each one of these points. So at A, this means that we have pure acetic acid, or not pure, but that's the only thing that is in there. We haven't started adding any base yet. So our major species is HA. At our half equivalence point, what's important here is that our pH value is equal to the pKa value. So when we do a titration, we first get to the equivalence point. We can back up to the half equivalence point if we've been recording the data and go, hey, that's my pKa value. At this point, we have exactly equal concentrations of HA and A-. At the equivalence point, we have consumed all of the HA, so that all we have left is A-. So this is our equivalence point. And the reaction is complete. We've used equal number of moles of acid and base. At D, we still have A- remaining. And then we begin to add excess hydroxide. So our A- stays constant from this point on, but we just keep including or increasing the amount of hydroxide ion. Okay, that is it for titrating the weak acids with the strong bases. Let me make sure everything's completely on screen there for you to see. All right, we are done.